Okay, get this. You and I are about to dive into the deep end of deep time. We're talking fossils,
Yeah.
the geologic time scale,
Yeah.
and the mind-blowing origin of life itself.
Right.
Buckle up.
And you've brought some fascinating sources.
I did.
What I find truly captivating is that we're going to be handling evidence from billions of years ago.
Right.
Imagine
Oh,
holding a fossil.
Yeah.
That's a snapshot of the world from before.
Right.
Well,
Okay.
almost anything we know.
Right. It's like time travel.
It is.
But instead of a DeLorean,
Yeah.
we have these ancient remnants.
Absolutely.
Speaking of which,
Okay.
can we talk about the different types of fossils? We've got bones, sure, but what else is there?
You've hit on a key point.
Okay.
People think fossils and picture dinosaur skeletons,
Right.
which are incredible, don't get me wrong.
Sure.
But the source image,
Uh-huh.
slide 1 from Fossil Evidence of Life, shows us there's a whole world beyond bones.
So.
Ammonites, those spiral shells, were everywhere in ancient seas.
Oh.
Yeah. And trilobites.
Those bug-like things with all the segments?
Yes.
They kind of creep me out, not gonna lie.
I know, they look like something out of science fiction.
Really?
But those guys were around for almost 300 million years.
Wow.
Their fossils are like timestamps,
Okay.
helping us date rock layers all over the world.
Really?
Paleontologists get pretty jazzed when they find those.
Okay, that makes them slightly less creepy.
Oh, good.
So trilobites are like index fossils, right?
Yes.
They tell you what time period that rock layer is from.
Exactly. Think of them like limited edition sneakers.
Okay.
They were super popular for a specific time, then gone.
Right.
Find a pair today. They're vintage.
Yeah.
Same with trilobites and rock.
Oh, I see.
Slide 7 shows a few good examples.
Okay.
And speaking of time, how do we go from this rock feels old to knowing something lived millions of years ago?
Right, because it's not like fossils come with birth certificates.
Sadly not. That's where absolute and relative dating come in.
Okay.
It's all about the properties of atoms. Radioactive isotopes decay at a predictable rate,
Uh-huh.
like a clock ticking away for eons.
Wow.
By analyzing how much of these isotopes are left in a fossil,
Yeah.
we can figure out its age.
No.
That's absolute dating, our precise time machine.
So we can get an actual year.
Yes.
Like this trilobite is 520 million years old.
Exactly. But sometimes we use relative dating,
Okay.
especially when dealing with really, really old fossils.
Got it.
It's less about specific years and more about sequence.
Right.
Like this fossil is older than that one because of its position in the rock layer.
Makes sense.
It's all about understanding the layers of time,
Layers of time.
much like a cake.
Like a cake. So older fossils are at the bottom, younger fossils on top, like the law of superposition.
Exactly.
Gotcha.
It's like stacking those pancakes on a Sunday morning.
Yeah.
The first one cooked is always at the bottom.
Right.
Now, this only works if the layers haven't been disturbed, like shaken up by an earthquake or something.
Mhm.
Slide 8 from Fossil Evidence of Life illustrates this really well.
I'll have to check that out.
You should.
So we've got our dating methods,
Yes.
but not everything becomes a fossil, does it?
Sadly, no.
It's got to be pretty rare when you think about how many things have lived and died on this planet.
You are incredibly right.
Yeah.
It's estimated that less than 1% of all organisms that have ever lived become fossilized.
Really?
Talk about exclusive.
Wow.
Slide 9 from the Fossil Evidence of Life outlines the perfect storm of conditions needed.
What are those conditions?
It's a long shot.
So walk me through it.
Okay.
What needs to happen for something to go from regular dead to fossilized celebrity?
First, you need a quick burial.
Like a mudslide.
We're talking mudslide, volcanic ash, something dramatic to seal the deal and protect the organism from scavengers or decay.
Wow.
Then, over a really long time, minerals in groundwater slowly replace the original organic material,
Really?
essentially turning it to stone.
No way.
Permineralization is the scientific term. That's the one that creates petrified wood, right?
Permineralization. It's
Mhm.
always tripped me out to think that wood can literally turn to stone.
It's wild, isn't it?
It is.
And it's not just wood.
What else?
We find permineralized bones, teeth, even soft tissues in some cases.
Really?
Slide 11 shows a cross-section of permineralized bone,
Uh-huh.
and the detail is amazing.
What kind of detail?
You can see individual cells.
Get out.
It's these details that give us those incredible glimpses into the past.
So fossils are rare.
They are.
They can be formed in a bunch of different ways, and
Yeah.
they give us these snapshots of life throughout time.
Exactly.
What I'm gathering is it's a pretty amazing field to be in.
It absolutely is. And speaking of amazing, you can't talk about the history of life on Earth without talking about the Cambrian explosion.
The what?
It's this period about 540 million years ago when life seemingly went from 0 to 60 in the blink of a geological eye.
Okay.
Slide 12, from Fossil Evidence of Life, shows a dramatic increase in diversity.
So picture this. Life has been around for a while,
Yes.
but it's pretty basic.
Uh-huh.
Single-celled organisms, maybe some simple multicellular stuff.
Yeah.
And then, bam, the Cambrian explosion hits.
Right.
And it's like, evolution discovered a nitrous oxide boost.
That's a fantastic way to put it.
Yeah.
Suddenly, we see this huge diversity of complex life forms appearing in the fossil record.
Wow.
It's like evolution decided to throw a massive party and everyone got an invitation.
Amazing.
We're still trying to figure out what exactly caused this sudden burst of life, though.
Really?
That's one of the biggest mysteries in paleontology.
Okay, I'm definitely going to need to hear more about this Cambrian explosion.
You can do that.
But before we dive into that,
Okay.
there's another big event we have to talk about.
What's that?
The dinosaurs. We all know how that story ends, right? It's a real bummer for the dinos.
It is.
But here's where it gets really interesting.
Okay.
The extinction of the dinosaurs paved the way for mammals
Right.
and eventually us. It's like that old saying,
What's that?
when one door closes.
A giant space rock smashes it open, leading to a whole new ecosystem.
Exactly.
But in all seriousness,
Okay.
the KT boundary,
Uh-huh.
that point in the fossil record where the dinosaurs disappear, is chilling.
Really?
Slide 13 shows the iridium layer,
Okay.
evidence of that massive asteroid impact.
It's wild to think that a single event could have such a profound impact on life on Earth.
It is.
But I guess that speaks to the interconnectedness of everything, right?
Absolutely.
Wow.
And this might sound odd,
What's that?
but thinking about these huge ancient events always makes me reflect on those tiny details we were discussing.
Like what?
Those premineralized fossils, with their incredible detail.
Right.
They wouldn't exist without the right conditions,
Yeah.
the right minerals, the right timing.
Uh-huh.
It makes you appreciate the fragility of it all.
You're right.
Yeah.
It's like winning the lottery, but for fossils.
It is.
Okay, so we've gone from monstrous dinosaurs to microscopic cells preserved in stone. Can we switch gears now and talk about how life actually began? That feels like the ultimate mystery.
It truly is one of the biggest questions in science.
Right.
And the source material you've got dives into three major theories:
Okay.
the primordial soup, panspermia, and hydrothermal vents.
Okay.
Each one tackles that leap from non-living matter to the very first life forms.
Let's start with the primordial soup, since that one seems to be the most well-known.
Okay.
I remember learning about it in school.
It's a classic.
Yeah.
The basic idea is that early Earth's oceans were like a simmering broth of simple organic molecules.
Really?
Think amino acids, nucleotides,
Okay.
the building blocks of proteins and DNA.
Right.
Then, energy from lightning strikes or UV radiation provided the spark,
Mm-hmm.
causing these molecules to react and form more complex structures.
So like a giant planet-sized pot of primordial chicken noodle soup,
Exactly.
but instead of noodles, we get life.
Exactly. Now, while the classic primordial soup theory has its merits, a lot of scientists today believe that those crucial reactions were more likely to occur in a more localized, energy-rich environment.
Okay.
Which brings us to hydrothermal vents.
Okay, so those are those underwater geysers, right?
Yeah.
They're like volcanoes, but under the sea.
Yes.
I remember seeing pictures of them. They're surrounded by these crazy life forms, even in the deepest, darkest parts of the ocean.
Exactly.
Wow.
Those vents spew out heat and chemicals from Earth's interior,
Uh-huh.
creating these little pockets of energy and nutrients.
Okay.
And the cool thing is,
Yeah.
a lot of those chemicals are the same ones we find in living cells today.
Oh, wow.
So it's not a huge leap to imagine that early life could have gotten its start in these environments.
So the primordial soup theory gets an upgrade.
You could say that.
Instead of a giant pot, we're talking about a network of underwater hot springs brewing up the ingredients for life.
Right.
That's pretty cool. But what about the third theory, panspermia?
Yeah.
That one always sounded a bit out there to me.
It's definitely the most out of this world theory.
Oh, really?
Literally.
How so?
Panspermia proposes that life didn't originate on Earth at all,
Wow.
but instead hitched a ride on a comet or asteroid from somewhere else in the universe.
So, like, alien microbes hitching a ride on a space rock. I can see why that one gets people talking.
It does.
But is there any actual evidence to support that?
It's tough to prove definitively, but there are some interesting clues.
Such as?
We found organic molecules, like amino acids, in meteorites that have landed on Earth.
Wow.
And Some scientists believe that certain hardy microorganisms, like tardigrades, could potentially survive a journey through space.
Really?
Yeah.
Wow, so it's not completely impossible.
No.
But let's get back to Earth for a moment.
Okay?
We've talked about the building blocks of life.
Yes.
But how did those building blocks actually assemble themselves into the first self-replicating organisms? That feels like a huge jump.
Absolutely. And that's where things get really interesting. Remember how we talked about RNA being like DNA's cooler, more versatile cousin?
Yeah, the one that can store genetic information, AND, catalyze reactions, right? Like a multitasking molecular machine.
Exactly.
The RNA world hypothesis proposes that early life might have relied solely on RNA to do both of those jobs.
Right.
It's a really elegant solution to the chicken and egg problem of DNA and proteins. Which came first? Well, maybe neither.
Yeah, it's a really fascinating idea.
So RNA was the original MVP,
Uh-huh.
paving the way for the more specialized roles of DNA and proteins later on. I
Right.
like it.
Yeah.
But how did scientists even begin to test these theories about the origin of life?
Well,
Did they try to recreate it in a lab?
it's exactly what they did.
Really?
One of the most famous experiments was the Miller-Urey experiment,
Okay.
conducted in the 1950s.
All right.
They recreated the conditions of early Earth's atmosphere in a lab.
What were those conditions?
Methane, ammonia, water vapor, hydrogen gas,
Okay.
and then zapped it with electricity to simulate lightning strikes.
And what happened? Did they
Right.
create life?
Well, not quite life, but they did manage to produce amino acids, the building blocks of proteins.
Get out.
It was a major breakthrough,
Yeah.
showing that the basic components of life could arise from simpler molecules under the right conditions.
Okay, so no Frankenstein's monster.
No.
But they did manage to create the ingredients for life in a lab.
Right.
That's still pretty impressive. But enough about single cells.
Okay.
How did we go from those simple beginnings to the complex, multicellular creatures we are today? That's a giant leap.
It really is mind-blowing.
Yeah.
We're talking about going from single-celled organisms to creatures with billions,
Right.
even trillions of cells working together.
So did these early cells just decide to team up?
You're actually closer than you think.
Really?
One prevailing theory is the endosymbiotic theory,
Okay.
and it's a wild one.
How so?
Imagine this. An early cell engulfs another cell,
Yeah.
but instead of digesting it for lunch, they strike up a partnership. This is likely how we got mitochondria,
Mitochondria.
those tiny powerhouses in our cells.
Right.
They were likely once free-living bacteria.
Hold on. So we're talking about a cell-eat-cell world?
Yes.
And sometimes, instead of a gruesome ending, they start a microscopic commune.
Exactly. And this wasn't a one-time thing.
Really?
The chloroplasts and plant cells, the ones that do photosynthesis,
Right.
they're also thought to have originated from a similar symbiotic event.
So we're all just products of ancient cellular collaborations.
In a way, yes.
That's incredible. It makes you look at a houseplant in a whole new light.
It does, doesn't it?
Right. I'm never looking at my ferns the same way again.
Yeah.
So from a primordial soup to symbiotic cells, are we starting to see those Cambrian explosion creatures pop up yet?
We're getting there.
Yeah.
But first, those single-celled pioneers had to pave the way.
Okay.
And one of the most important developments was the evolution of multicellularity.
Okay.
Now, this is a tricky one.
How so?
Because it's believed to have happened multiple times, independently, across different lineages.
Pull up multiple times. You're saying multicellular life is like that one-hit song that keeps getting covered by different artists.
Perfect analogy.
Yeah.
And just like each artist brings a unique spin, each lineage that evolved multicellularity found its own path to success.
Wow.
We see it in plants, fungi, animals.
Really?
It's amazing.
So it happened more than once.
It did.
That's wild. What were the advantages of going multicellular?
Well, for one, it allowed organisms to grow larger and more complex.
Right.
They could also specialize, with different cells performing different functions.
Right.
This paved the way for the incredible diversity of life we see during the Cambrian explosion and beyond.
Okay, let's talk about that Cambrian explosion then.
Okay.
It sounds like a pivotal moment in Earth's history.
It was.
What can you tell me about it and what caused it?
Picture this. It's 540 million years ago.
Okay.
Life up to this point has been pretty chill.
Okay.
Mostly simple organisms just vibing. But suddenly, bam, the Cambrian explosion hits.
happened?
It's an explosion of new life forms, an evolutionary party.
Wow.
Trilobites hit the scene, along with early ancestors of everything from jellyfish to vertebrates.
Okay, that's a serious guest list.
It is.
What sparked this sudden burst of diversity? Was it like a cosmic light switch flipping on?
It's a question that keeps scientists up at night.
Really?
The exact trigger for the Cambrian explosion is still debated.
Okay.
Some point to rising oxygen levels.
Okay.
Others argue it was a change in ocean chemistry,
Okay.
or maybe even a combination of factors,
Right.
whatever the cause. This period fundamentally changed the course of life on Earth
Right.
and set the stage for everything that came after.
Wow, that's incredible.
It is.
It makes you realize that the world as we know it, even with all its complexities, is built on these ancient foundations.
Yeah.
These incredible events from billions of years ago have shaped everything.
That's exactly right. And this exploration of life's origins, it's about so much more than just dinosaurs and fossils.
What else is it about?
It's about understanding our place in this vast, ancient universe.
It's about perspective, right?
It is.
When you realize how life on Earth has persisted through mass extinctions,
Yeah.
environmental upheaval, and
Right.
even asteroid impacts,
Uh-huh.
it puts things in perspective.
Absolutely. It's humbling, and it makes you realize that we're part of something much larger than ourselves.
Wow, okay.
The story of life on Earth is a testament to resilience,
Uh-huh.
adaptation,
Right.
and the constant dance between opportunity and chance.
Wow, I like that.
Yeah.
Okay, I have one final question for you.
Right.
We've talked about life emerging from primordial soup.
Yes.
We've discussed panspermia, those tardigrades hitching rides across the galaxy.
Right.
Is there anything that really surprises you about life's origins?
You know, what constantly blows my mind is the sheer improbability of it all.
What do you mean?
The fact that we, conscious beings, capable of contemplating our own existence, are here at all.
Yeah,
It feels like winning the cosmic lottery.
it does, doesn't it?
Yeah.
Well, that's a beautiful note to end on.
It is.
It has been quite a journey. From the tiniest fossils to the biggest mysteries of the universe, what's the one thing you hope our listeners walk away with?
Never stop questioning,
Okay.
and never lose that childlike sense of wonder.
Okay.
The story of life is full of incredible chapters, and who knows what mysteries we'll uncover next.
Perfectly said. Thanks for joining us on this deep dive into the origins of life.
Act pleasure.
Until next time, keep exploring.